Hi, this is Alessio and welcome to lecture number 8. Today, Hi, this is Alessio. Welcome to lecture number 7, which is cloud technologies. This is just an introduction to topics which you may find interesting and that you may want to explore a bit more in the future. The agenda for today, we're going to look at a cloud economics primer. We're going to look at the reference model. We're going to learn a little bit about scalability and also availability. So, first of all, what is cloud computing? Cloud computing refers to both the applications delivered as services over the internet and the hardware and system software in the data centers that provide those services. So, if we want to talk about it, we can refer to as this immense data storage, data computation services offered through an internet provider, through the internet services. So nowadays, we start to think about everything being as a service. For example, we don't really create or buy hardware anymore. We create virtual machines, or we use Docker, or we use online databases. We rarely go and create our own systems. We always borrow from other people. So the concept of everything as a service, also known as XaaS, which stands for as a service, deeply permeates cloud computing. In essence, anything in the IT stack can be delivered as a service. 3 simple criteria can be used for a cloud computing service. The service is accessible via web browser or the web API. There is zero capital expenditure is necessary to get started, and you pay only for what you really use. What are the benefits, especially economically, at a glance? The key commercial benefits of leveraging cloud computing offerings are the following. 1. Reduction of capital cost associated with the IT infrastructure. Elimination of the depreciation of lifetime of cost of capital IT assets. You basically buy something and the hardware doesn't really lose its value. That's how normally it is. You pay for something, you pay for CPU cycles, you pay for actual things happening. You don't care on what hardware it is running. It is not yours to own. It belongs to somebody else who is leasing it out to you somehow. Replacement of software licensing with subscriptions, and reduction of maintenance and administration costs to the IT infrastructure. So the cloud, we can say that it's a cloud economic revolution because it really changes how we do things, how we go from old world to a new world. So what are the advantages of this huge change? Well, first of all, there is no need of large initial investments to cover capital cost. Second, by not owning IT assets, organizations do not incur in their depreciation. Other related operation costs are reduced as well, like the maintenance. The IT infrastructure can be sized to the wellness of the business. If your business is going really well, get more. If you're not going so well, perhaps cut it down so you can cut the cost. The growth in both size and functions can be incremental, and the transition can be incremental while assets get dismissed. So you can increase, but you can still dismiss your assets. So what are the learnings from this very short but insightful economics primer? First of all, capital and operational cost. Cloud computing transforms most of the traditional IT costs into operational costs, thus opening new opportunities for enterprises, startups, and individuals. What does that mean? Startups do not need to invest money into hardware. They don't have to buy $100,000 worth of machines that they may not be using because maybe they will fail. They can just go and set up a few virtual machines and scale them up as they feel like. We start to use computing power services the same way we look at electricity. Then, economic opportunities for the cloud offerings. Both service consumers and providers benefit from the utility-based model that defines cloud computing. Service consumers can reduce cost and become more agile. Service providers can leverage the economics of scale, meaning that we start small and we scale up as much as we want. Profiles and pricing models. Enterprises, startups, and single individuals can benefit from cloud computing offerings in different ways, based on the new concept of pay-as-you-go. Services are priced according to the different models. So, then, what is the cloud reference model? The cloud reference model, and this keeps on growing, are all at a high level the kind of different services which are offered. So cloud computing offerings, services, and solutions are better understood by considering the type of capabilities provided. We have IaaS, PaaS, SaaS, FaaS, and you will find that we start using this AaaS as for everything. We have like AI as a service, database as a service. So what are these main ones that we're looking at now? First of all, we have infrastructure as a service, core infrastructure and hardware. This refers to actual machines, to the building blocks of your system, virtual machines, storage, and networking. Then we have the platform as a service, which is runtime, environments, and platforms. Runtimes and development runtimes, environments for specific technologies or languages designed to host your applications. What that means that you're slowly losing the control because you don't actually build your applications on top of a virtual machine, but on top of a silo's hardware, which has been virtualized for you. It's a runtime environment. So you only see that environment. You don't have to worry about the machine. You don't have to worry about how much memory the machine has. You know that you have that environment. You deploy your application on it, and you just run it. That is called platform as a service. Then we have the SaaS, which is the standard way of people want to deliver things nowadays, which is software as a service. There are either applications accessible through the internet that replace existing applications on your desktop, or services that expose features that can be integrated in applications. The classic one is Gmail. Gmail is a classic software as a service. What can you do? You use it as your mailing service. Can you go and change it? You can just customize it a little bit. So normally, software as a service are all the softwares which give you the ability to just do things as you would normally do. For example, you can go and code online, you can go and design online, you can go and create your PowerPoints online. Those are all software as a service. And then we have the next one, which is the functionality or serverless as a service. This is where our software development becomes so small that we don't even write software anymore. We just write functions, individual functions that we call and we try to interconnect with one another. So one type of cloud that we are exploring just here is the public cloud. Public cloud constitutes the first incarnation of the cloud computing concept and its canonical implementation. First of all, it is open. The cloud is available through the internet from any device, every location, and any time. That's why we say it's open. It's distributed. To serve a large number of users, public clouds are composed by geographically dispersed data centers. That's why we have location data centers everywhere in the world. We, for example, have AWS data centers in Sydney, or we have them in China, we have them in America. Depending on where we are, we want to use the closest one because lag is still a thing. So we want to use the closest. Infinitely scalable. Public clouds give the illusion of infinite scalability because of the large number of resources. And they're multi-tenants because most public clouds are designed to serve multiple organizations at once whose applications might actually share the same infrastructure. This is done to decrease the cost. Okay, so here we have the actual look at what the cloud offerings look like. The infrastructure as a service, the platform as a service, and the software as a service. The one thing that we can say is that going down at the bottom, we're closer to the CPU. Going up, we're closer to the actual application. What does that mean? It means that the green part is what is managed by the service provider. The blue part is the actual effort that we have to do. So in infrastructure as a service, for example, We have to worry about the maintenance of the operating system, the runtime installation, the security, the instance monitoring, and then develop the application itself. If we move to platform as a service, we can see that we lose all of that part, which is the instance monitoring, security, runtime, and the maintenance, meaning that we now have a lot less control, but we can dedicate more time to actual software development. And then we got even one further, which is the software as a service, where we only have the application consumption. So we actually do not have any power to do anything apart from consuming the application itself. So how can developers benefit from the cloud? If we think about the traditional development, we can see that we had to do all of these things to develop something. And that's really boring. There are so many steps there that we as developers, perhaps 10 years ago, we had to do over and over and over again, and just waste of time. This is what the cloud allows us to do. We are able to just look at the sweet spot. We can just go and enjoy developing and creating applications. We don't have to worry about all of the maintenance, operating system, installing things, taking care of the hardware or anything like that. So if we look at the actual process of how we create applications, we can say that we want to take care of the core logic. We want to know what we have to do. This is the actual sweet spot. It's the implementation, the design, the planning, and the inception. We don't want to worry about the testing. We don't want to worry about the deployment. We don't want to worry about the maintenance. That's what we as developers like to do. Everything else can be handled by the actual platform. Scalability and availability. These are the two key concepts that you can understand about cloud. We're not going to go into too much detail about this, but it is something that is nice to know for the future or if you want to explore cloud. First of all, we have this illusion of scalability. The illusion of scalability is basically this thought that we believe that in the cloud there is infinite resources, so we can create as many images as we want, as many servers, but the truth is it's not, because we have finite resources. So grow as much as you want. From an application development perspective, the illusion of infinite scalability is perhaps the most attractive feature for developers and engineers. We don't have to worry. We can just scale up as much as we want. That's why we really like this cloud concept. If today we have 10,000 users and tomorrow we have 1 million, I click a button and my whole infrastructure is now 100 times bigger. We can do it reliably. Together with the almost immediately availability of the infrastructure, platform and services scalability ensures that not only non-trivial systems can be more rapidly built, but also that they are properly engineered. Such systems can sustain challenging loads when put into production. This is another very important part. What we do here is basically fully engineer to sustain heavy loads. If I had to, for example, take care of scaling from 10,000 to 1 million users, I wouldn't know where to go. Probably I could, but I wouldn't have to waste weeks and weeks in trying to think of everything that could happen. Clouds instead are developed in a way so that they are meant for scalability. They are meant to automatically adjust. So scalability, we have two types. We have the horizontal scalability and the vertical scalability. Scalability can be achieved by either increasing the capacity of set of features which are already used, that's the vertical scalability, or by parallelism, which is adding more resources of the same type. That is horizontal scalability. So let's imagine that we have one service. Let's imagine that all of a sudden we need more power to actually work on a particular algorithm. Let's say that we created an AI server. AI servers, the actual, let's say, an inference, is dependent on the GPU. The better the GPU, the faster, the less time it will take to actually run the inference. That's something where vertical scalability will do better. So a larger CPU, a larger memory, or larger GPU will make the load easier to take care of. But what happens instead if My web server doesn't need to do complex things, but it needs to handle many things. Well, having a larger CPU or a bigger memory will not help me at all. So that's when we go for the horizontal scalability. Horizontal scalability is when we replicate the same resource with more instances of it. So for example, if we want to increase the portability of a database, we can increase the number of database instances so that we can scale it out. Or if we have a web server, we can create more web servers. So from a development perspective, we have both advantages and disadvantages. Vertical scalability is easier to implement and very often is implemented independently from the application code. It often translates in changing the performance parameters of the environment hosting the application. For example, increasing the power, memory, or physical or virtual hardware. The primary disadvantage is this capped at the amount of improvement that can be obtained from the service interruption. Oh, and it has service interruption. If you have to change the CPU, you can't do it without turning it off. The horizontal scalability instead actually is much more complicated. It touches both the hosting environment and the application core logic. Even though more concentrated on the latter, it enables the implementation of additive capacity requirement. This is more complex to implement, but it is potentially uncapped and does not require service interruption. So what does that mean? If we have the vertical one, our application doesn't need to change its behavior. It's just going to find more resources when it gets there, when it gets called. The horizontal scalability instead, let's say that we have a request being made to the server, but now you have 10 servers. So how are you going to handle it? Who's going to pick it up from that server? We need to start making things more smarter. So we have to actually manage all of these 10 servers working together. Then we have the application demand profiling. We're going to really quickly just touch on this because it is important to understand it, but not vital for now. So how do we choose how much we're going to be using? Well, we're looking at things, for example, constant demand, demand which is growing at a constant rate, and in regular demand. How do you know how much resources to put into place? Well, it depends what you're working on. We need to understand how demand works. The first one, constant demand, almost never exists. It's a normal horizontal line that never exists. If that was constant, we would just say we just need to put enough resources in order to satisfy that. What if the demand keeps on growing at a constant rate? Well, that could happen, but once again, this is very unlikely as well. Even the best company eventually will slowly reach a plateau and then stop, maybe die. So we can't just keep on increasing the resources. And then finally, we have the irregular demand, which is a normal demand that we have every day. And you can see it. Basically, the demand changes over time. We have things, for example, let's say Uber. We know that let's say Uber Eats is much simpler. We know that Uber Eats will have peaks between 11 and 2 p.m. and then probably between 5 and 7 p.m. That's because that is lunch and that is dinner. So then what do we do about it? How can we actually take care of it? Well, we can look at elastic capability. If we say that in order to sustain the actual load, we need X amount of resources, we can try to profile it, and we can say that as the load increases, we automatically increase the resources as well. When the load decreases, then we decrease the resources as well. We can say that at lunchtime, we're gonna have 10 servers up and running, and then at 2 p.m. we're slowly going to kill the servers one by one. And the good thing about using a cloud is that we have this elastic scalability inbuilt. We can profile it and we can set it up automatically so that we automatically spin up or kill off servers as we go. Then we have the availability. Availability is a concept of making sure that things do work, or when you click the server, you actually have something happening. In the normal world, we can say that we use a 5 nines system, a 5-9, let's say, reassurance. What does that mean? It means that normally a system should be 99.999% up. It should have a 99.9999 uptime, meaning that 99.9999% of the times when you click it, it should be up and running. So that is what availability is. If we have a server, a normal server that is hosted somewhere, if it dies, it's probably very hard to bring it back. But if it's on a cloud, well, the system normally takes care of restarting it or finding a way to serve it. So here we just have some calculations of how you could go and do it. What is availability, mathematically speaking? It's the uptime divided by the uptime plus the downtime. Meaning that, and I believe I have it here, that we can have at the most 5,000 minutes of downtime in 1 year. And once again, because we're talking about cloud and, well, hardware or regardless things, there are failures that can happen. Things can go wrong. And we need to understand also what it is that we can fix and the things that we cannot fix. So there are failures which are under our control and we can do something about it. We have failures which are partially under our control. And these have some strategies. And sometimes it's just mitigation strategies, like we can't really fix them or avoid them, but we can try to, in case something happens, we can try to lower the damages. And then we got the failures which are completely out of our control. What happens if the server, the data center where all of our things were stored, gets nuked and it disappears from the face of the earth? We can't really do much about it. But having said that, it is true that when the Twin Towers got hit on September 11, the downtime was actually only 6 minutes. 6 minutes was the time that it took the IT department to reroute everything to London. So quite amazing. Of course, not a good day, but that is what it means to be on a redundant IT infrastructure. And looking at this diagram, we can see that on a normal application, all of these things can go wrong. All of this, the load balancer could die, your application could die, your message queue could die, your database could die. These are all the things that can die. So what can we do about it? Well, one thing that we can do is we can think about creating a redundant design. So for example, front-end nodes, we can replicate nodes. And we use the rule of thumb, which is the n+1. n+1 means that we have n number of instances, which is the minimum required, plus 1, at least plus 1. Meaning that, for example, if we have 3 front-end nodes, we have a backup one, so we have 4. If we have a message queue, if we have 2 message queues, we just make sure to keep 1 on standby, so we have 3. And so on, and so on, and so on. So this is the basic behind redundant design, which is about making sure that we do have spare resources ready to go if the need comes. Is it cheap? No, but it's better than having your complete system down. So that is all for today, and thank you. Hope you're liking cloud, and I do hope that you guys can perhaps join my class next year. Bye bye.